Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, I was standing outside the other night. It was a really clear sky. No moon. And I was doing that thing we all do. I was just looking up at the Milky Way.
Mm-hmm.
And when you look at that sort of band of light, you know the numbers. You've heard them a million times. There are, somewhere between 100 and 400 billion stars just in our galaxy alone.
An almost incomprehensible number.
It really is.
Mm-hmm.
And, you know, statistically, even if life is a 1 in a billion shot, the sky should just be buzzing with activity. It should be like Times Square on New Year's Eve up there.
But it's not. It's quiet.
It's dead quiet. And that's the Fermi paradox, isn't it? It's the ghost that haunts modern astronomy.
It is. The great silence. The question that underpins everything we do when we look at the stars. Where is everybody?
Exactly. It's the question that keeps us up at night. And for the last, 60 or 70 years, ever since Frank Drake first wrote down his famous equation, we've been trying to answer it. We've been listening.
With massive radio telescopes, yeah.
We've been scanning for radio waves, looking for Dyson spheres, hunting for laser pulses from some advanced civilization. And the silence is just, it's deafening.
It's profoundly unsettling because all the math, all the logic, it says we shouldn't be alone.
Right. And usually when we try to explain that silence, we tend to blame, biology. We say, maybe life is just incredibly rare. Or maybe the jump from single-celled to multi-celled life is the big hurdle.
Or we blame politics. The idea that civilizations get powerful enough to invent nuclear weapons and then they wipe themselves out before they ever get to the stars.
Great filter. But today we're looking at some research that points the finger at something else entirely, something so mundane, so dirty and so terrestrial, we almost never think about it in the context of aliens.
Yeah, we're not talking about DNA and we're not talking about nuclear war. We're talking about rocks.
Specifically, we are talking about coal.
It sounds almost ridiculous when you say it out loud, doesn't it? That the key to interstellar communication, to the highest tier of technology, might depend on this black, sooty rock that we are currently trying, desperately to stop using.
It feels completely counterintuitive. But this new paper from the International Journal of Astrobiology, led by Lincoln Thais, it makes a really compelling, almost disturbing case. They argue that we might be alone not because life is rare, but because the Industrial Revolution is a kind of geological lottery ticket that most planets just never get to cash in.
Precisely. The core premise is that you can have a planet absolutely teeming with life. You can have smart, philosophical, artistic creatures. But if they don't have access to massive, easily accessible, energy-dense deposits of fossil fuels, and specifically coal, they will never break through a certain technological glass ceiling.
They'll never build a radio telescope.
They'll never build a radio telescope. They will never say hello.
So our mission today is to really unpack this idea. We need to understand why a lump of coal is actually a piece of advanced technology in disguise, why our planet Earth got lucky enough to have it, and what this all means for the search for extraterrestrial intelligence.
We're going to be talking about something called the energy ladder. And I should warn you, this might make you look at something as simple as a rusted steel beam or even a cloudy sky with a completely different level of respect.
Okay, let's start with the basics then. I want to play the skeptic immediately because I know you listening are probably thinking it. I'm certainly thinking it. We're talking about starships, supercomputers, massive SETI arrays, high-tech stuff. And you're telling me the prerequisite for all of that is burning dead plants. It feels like we're mixing up our eras. Why is the dirty, primitive stuff a hard requirement for the clean, advanced stuff?
It's a totally valid skepticism. It feels like a paradox.
Mm-hmm.
But to really get it, we have to look at what these authors call the energy ladder. And you have to think of technological progress not as some, smooth upward slope where you just slowly get smarter and build better things.
Right.
Think of it as a series of very high, very distinct steps. To get to the top, where you have silicon chips and satellites and solar panels, you have to be standing firmly on the step just below it.
Yeah.
And the step right below our silicon age is the steel age.
Steel. Okay, I get that.
Okay.
I mean, we use steel for everything. If I look out my window right now, every building, every car, every bridge, It all involves steel. But humans were making metal long before the Industrial Revolution, right?
Of course.
We had the Bronze Age, we had the Iron Age. We were making swords and plows using charcoal from wood fires thousands and thousands of years ago. Why couldn't an alien civilization just keep doing that? Why couldn't they just scale that up and build a radio telescope using wood-fired iron?
And this is where the physics gets really mean. It all comes down to two things: scale and heat. Yes, you can smelt iron with charcoal. Humans did it for millennia. But charcoal, as a fuel source for an industrial civilization, has two fatal flaws.
Okay, what are they?
First, it's just not energy dense enough. You have to burn a staggering amount of forest to get a relatively small amount of metal. You would effectively have to deforest your entire continent just to build one major city. The energy return on investment is terrible.
Right, you run out of fuel pretty quickly.
Very quickly. But the second problem is a structural one, and this is the one people almost never think about.
Structural, you mean the charcoal itself?
Exactly. To mass produce the kind of steel you need for skyscrapers or massive ships or launch pads, you need a blast furnace, a massive towering structure, sometimes 10 stories high, that you feed iron ore into from the top.
Okay.
If you fill a giant blast furnace with regular wood charcoal and then dump tons and tons of heavy iron ore on top of it, what do you think happens to the charcoal at the bottom?
It would get crushed.
Yeah.
Because charcoal is brittle, it's just burnt wood.
It gets crushed into dust, it crumbles, and when that charcoal turns to dust, it chokes the fire. Air can't circulate up through the stack. The combustion process just stops. The furnace dies.
So you physically cannot build a massive blast furnace using wood charcoal.
You can't. You hit a hard physical limit on how big you can go, which means you hit a limit on how much steel you can produce. Your civilization's growth literally crumbles under its own weight.
So you're saying you can't build the infrastructure of a modern city with wood? The fuel itself breaks.
Right. You are stuck. You'll hit a physical limit on production. To go bigger, to get hotter, you need a fuel that is harder, hotter, and stronger. You need coke.
And just to clarify for everyone, we are not talking about the soda.
No, definitely not. Coke, C-O-K-E, is a processed fuel made from coal. You take bituminous coal and you bake it in an oxygen-free oven. This process, called coking, burns off all the impurities, the water, the tar, the volatile gases, and what you're left with is almost pure, concentrated carbon.
What's special about that?
It's hard, it's porous, and it burns incredibly hot and consistently. But most importantly, it's strong. It has what engineers call crush strength.
Crush strength.
It can support the weight of hundreds of tons of iron ore stacked on top of it in a blast furnace without crumbling into dust.
That is such a specific, mundane detail. The crush strength of the fuel determines the size of the civilization.
It really, really does. So coke allows you to build the mega furnaces. The mega furnaces give you cheap, high-quality steel in absolutely massive quantities, and that is the gateway. This is the domino effect that the paper describes. And I think it's worth walking through this chain because it's fascinating just how tightly connected it all is.
Okay, let's do it. Domino number one.
Domino one. You have massive and critically accessible coal deposits on your planet.
Okay, so step one is just the geology. You have to be born on a lucky planet.
Domino two. That coal allows you to create coke, which in turn allows you to create mass-produced steel.
Got it. Step two is the metallurgy. We now have the steel.
Domino 3. What is the single most important thing you make with that new high-strength steel? And it's not swords, it's not armor, it's drill bits.
Drill bits. Okay, that's unexpected. I was thinking maybe steam engines or train tracks.
Oh, those are hugely important, don't get me wrong. But the drill bit is the true pivot point of the 20th century. Because why do you need high-strength industrial steel drill bits to get to Domino 4, deep pressurized geological reserves of oil and natural gas?
Oh, okay. I see where this is going. It's all about depth.
It is exactly about depth. The coal that kicked off our Industrial Revolution in places like England and Pennsylvania, it was often right at the surface. You could literally pick it up off the ground or dig it out with a shovel and a bucket. It was the low-hanging fruit of energy.
Right. You didn't need high tech to get the first energy source.
Exactly. But oil isn't like that. You don't just, find a pool of crude oil sitting in the woods.
No, it's deep underground.
Very deep. The crude oil that powered the 20th century, the stuff that gave us cars and planes and massive electricity grids, is usually trapped thousands, sometimes tens of thousands of feet underground. And it's often under incredibly hard capstones of rock, like granite or limestone.
And you can't get through that with a pickaxe.
You can't get to it with a pickaxe. You can't get to it with a wooden rig. You need hardened steel pipes and drill bits tipped with industrial diamonds or tungsten carbide to puncture the earth deep enough to tap that incredible energy source.
So if you don't have the coal to make the steel, you can never drill deep enough to get the oil.
And if you don't get the oil, you never get the internal combustion engine. You never get the petrochemical industry. You don't get the plastics and the insulators you need for advanced electronics. And ultimately, you never get the radio telescope.
So it really is a technological glass ceiling. You might have geniuses on your planet. They might know the math. They might understand the theory of radio waves. They might have the blueprints for a receiver sitting on a desk. But you physically cannot build the machine.
You can't. Because you lack the materials to extract the next level of materials.
You're stuck.
You are stuck in a wood and iron age. Maybe you build great sailing ships. Maybe you develop incredible clockwork mechanisms. Maybe you have breathtaking architecture using stone and basic metals. But you are not launching satellites. You are not building microprocessors.
That is a wild realization. We usually think of technology as just being about knowledge. If we know how to do it, we can build it. But this paper argues that technology is fundamentally material. It's resource dependent.
Knowledge without the calorie density to actually apply it on a massive scale is just philosophy. The authors argue that fossil fuels, and coal specifically, are the only energy source that is both dense enough and accessible enough to a pre-industrial society to bootstrap the whole system.
They're the starter fluid.
They're the starter fluid for the engine of civilization. Without it, the engine never turns over.
I want to push back on this, though. I feel like we're being very deterministic here. We're essentially saying there is only one path. But surely the universe is full of variables. Let's play devil's advocate, because I can hear the counter-argument screaming in my head right now.
Go for it.
We are humans. We were messy. We were inefficient. We burned the coal. We choked our cities with smog. We heated the planet. But couldn't an alien species just be better than us?
The green alien hypothesis, the eco-friendly ET.
Right. Couldn't they be smarter? Couldn't they look at a lump of coal, analyze the chemistry, realize it's going to mess up their atmosphere, and just say, you know what, no thanks? Why couldn't they skip the entire dirty phase and go straight to wind, water, solar, or geothermal? Why do they have to burn the rocks?
It is a very, very appealing thought. We want to believe that pollution isn't a necessary step. It comforts us to think there's a cleaner, smarter way. But the paper addresses this idea head-on, and they argue it's a classic chicken and egg problem.
How so? A chicken and egg.
Okay, let's look at a modern wind turbine, one of those big 3-megawatt ones. It looks clean, right? It's elegant, it spins in the breeze, generates electricity, no smoke. Beautiful. But what is it actually made of?
Well, the tower is steel. Massive sections of steel.
Hundreds of tons of high-grade steel, which, as we've already established, needs a blast furnace burning coke to produce. What about the blades?
I think there's some kind of composite. Fiberglass?
Usually carbon fiber or fiberglass resins. And where do those come from? They are petrochemicals. They are derived from oil and natural gas.
So the blades of a clean wind turbine are made of oil?
Essentially, yes. And that's not all. What's inside the nacelle, the generator at the top, it needs incredibly powerful rare earth magnets like neodymium to work efficiently.
Right.
Mining and refining rare earth metals is one of the most energy-intensive and chemically harsh processes we have. You have to move literal mountains of rock to get just a few kilograms of metal.
And how do you move all that rock?
With massive diesel-powered dump trucks and excavators, which are made of steel and run on oil. Do you see the problem? You cannot build a wind turbine with stone tools. You can't even build it with blacksmith's tools from the Iron Age.
You need the dirty machine to build the clean machine.
That is the catch-22. To build the clean energy infrastructure of the 21st century, solar panels, nuclear reactors, hydroelectric dams, you need an industrial base that is already capable of precision manufacturing, heavy global transport, and high heat metallurgy.
It's like trying to build a computer when all you have is a hammer and a log.
Solar panels are another perfect example. To make a modern photovoltaic cell, you need silicon that is 99.9999% pure. We call it electronic-grade silicon. To get silicon that pure, you have to start with quartz sand and melt it down. Do you have any idea how hot you have to get quartz sand to melt it?
I'm guessing pretty hot.
Around 3,500 degrees Fahrenheit, or about 1,900 Celsius. You cannot do that with a wood fire. You can't do it with a magnifying glass. You need massive industrial arc furnaces that consume incredible amounts of electricity.
And where does the electricity for those first furnaces come from in a developing civilization?
It has to come from something that burns. If you're a pre-industrial society, you don't have the solar panels yet to power the furnace to make the solar panels. It's a paradox. You have to burn the stored sunlight of the past, the coal, to build the technology that can catch the sunlight of the present.
So if you're an alien on a planet without coal, you might theoretically understand how a solar panel works. You could write down the physics, but you're trapped by the energy limitations of wood and muscle power.
Exactly. You can never generate the massive surplus energy needed to build the next rung of the ladder. You're stuck in an energy poverty loop. The authors are very clear on this point. An advanced technological civilization, what they call an ATC, must pass through a fossil fuel phase. They believe there is likely no shortcut.
Wow. That implies that every advanced civilization in the universe, if they exist, has had to deal with climate change. They've all had smog. They've all had their own version of Victorian London or 20th century Pittsburgh.
It becomes a universal filter. If you want to reach for the stars, you have to get your hands dirty first.
Okay, so we've established the need. An ATC needs coal to get off the ground. But here's the part that still confuses me. Coal is just dead plants, right?
Essentially, yes, it's fossilized terrestrial plant matter.
So if we assume that life is somewhat common out there, if we assume there are other planets with forests or jungles or whatever their equivalent is, wouldn't they all have coal? Why would this be a filter? If you have trees, don't you automatically get coal?
And here is where we pivot from engineering to geology. This is the part of the paper that really blew my mind. The answer is a resounding no. Just having trees does not guarantee you get coal. In fact, on Earth, the formation of the coal that powered our world was a bizarre anomaly. It wasn't the rule, it was the wild exception.
An anomaly. I always thought it was just what happens when trees die and get buried.
Not usually. Think about a forest today. A tree falls in the Amazon or even in your backyard. What happens to it over time?
It rots. You know, termites eat it, fungi and bacteria break it down. Eventually, it just becomes part of the soil.
Exactly. The carbon is recycled. It's released back into the atmosphere as CO2 by the decomposers. It doesn't get buried. It doesn't become a rock. But starting about 360 million years ago, during the Carboniferous period, something very different happened.
The Carboniferous, the coal-bearing period. I guess the name says it all.
It really does. There were two massive, unique factors that aligned perfectly to create something like 90% of all the coal we use today. 90% in one specific window of geologic time.
Okay, what was factor one?
Factor one was biological. Trees had just invented a new revolutionary molecule called lignin.
Lignin. That's the stuff that makes wood hard, right? It's what allows a tree to grow 100 feet tall without just flopping over like a piece of spaghetti.
Correct. It's the structural armor of the plant world. It's incredibly tough stuff. But when lignin first appeared in the evolutionary timeline, there was a problem. And here's the kicker. For about 40 to 60 million years, nothing on Earth knew how to eat it.
Wait, really? The bacteria couldn't digest it? The fungi?
The white rot fungi, the specific family of mushrooms and bacteria that are experts at breaking down wood today, simply hadn't evolved yet. There was a huge evolutionary lag. So when these massive primitive trees died and fell over, they didn't rot, they just sat there.
That is a wild image. A world where dead trees just pile up like garbage because nature hasn't invented the garbage disposal yet.
That's a perfect analogy. Imagine walking through a forest where every single tree that had fallen for the last million years is still there, just piled up, hundreds of feet deep in some places.
Yeah.
But that alone isn't enough to make coal. If they just sit on the surface, they'll eventually oxidize or dry out or burn in a forest fire.
So you need to bury them.
We need to bury them fast and deep. And that brings us to factor two, plate tectonics.
The moving continents.
Specifically, the collision of continents. During this exact time period, the supercontinent of Pangaea was forming. The ancient continents of Gondwana and Laurussia were smashing into each other in slow motion.
And that created mountains like the Appalachians.
It created mountains, yes, but it also created the opposite of mountains. It created deep, rapidly sinking basins right next to the new mountain ranges. They're called foreland basins.
Explain foreland basin for us.
Think of it like this. If you put a heavy weight on a mattress, the mattress sags down around the weight. When you build a huge mountain range, Its immense weight pushes down the edge of the tectonic plate next to it, creating a long, deep trough or basin.
Okay.
During the Carboniferous, you had these massive, swampy, tropical basins forming right next to the rising mountains. So these lignin-rich trees would fall into the water, sink into the anaerobic mud with no oxygen, and then be rapidly buried by tons of sediment and rock washing down from the eroding mountains.
So they were sealed off.
Preserved, perfectly sealed up from the air, then compressed by miles of rock above them, and cooked by the Earth's geothermal heat for millions of years. That specific pressure cooker environment is what turned the wood into coal.
And this only happened because of that specific combination. The wood-eating fungi weren't there yet, and the continents were smashing together in just the right way to create these burial pits.
Yes, and eventually, the fungi did evolve to eat lignin. The coal window slammed shut. If you look at the lush forests from the Jurassic or the Cretaceous, the age of dinosaurs, they didn't leave behind coal deposits that were nearly as massive or high quality as the Carboniferous ones.
Why not?
Because by then, the wood was rotting away on the forest floor before it ever had a chance to be buried. The cosmic garbage disposal had finally been invented.
That is incredible luck. So let's apply this to an alien planet. You could have a world with lush jungles that have existed for 1 billion years.
Yeah.
But if they never had that biological lag where the decomposers couldn't eat the trees, or if they don't have active plate tectonics to create those deep basins,
then the dead trees just rot. They return to the carbon cycle. They never form the dense, concentrated energy banks needed for an industrial revolution.
and the civilization on that planet is just out of luck.
They might have plenty of wood. They can burn it to stay warm and cook their food. But they will never find the thick, black seams of high-density coal needed to smelt steel and bootstrap a technological society.
It implies that active geology is a hard requirement for intelligent life to become technological life. A planet like Mars, for instance, Mars is mostly geologically dead, isn't it?
For the most part, yes. Mars has what geologists call stagnant lid tectonics. Its crust is one solid piece. It doesn't have plates crashing together and subducting and creating these deep burial basins. So even if Mars had dense forests billions of years ago, it probably didn't create the kind of deep, rich coal reserves needed for industry.
This really adds a whole new powerful layer to the rare Earth hypothesis. It's not just rare life, it's rare tectonics and rare fungi evolution.
But wait, because there is another layer to this onion. It gets even more specific. It's not just about space and geology. It is about time.
Time. What do you mean?
The paper raises an incredibly important question about what they call synchronicity. It's the race between evolution and geology.
Okay, explain that concept.
Think about coal like a slow-cooked meal, like a brisket in a smoker. You can't just put it in the oven and take it out 5 minutes later and expect it to be good. It takes time to be ready.
I'm hungry now, but go on. I'm with you.
The plant matter that gets buried starts as peat. Peat is okay. You can dig it up and burn it. People in Ireland and Scotland did for centuries. But it's wet, it's smoky, and it has a very low energy density.
Not nearly enough for a blast furnace.
Nowhere near enough. Over millions of years, the heat and pressure from those overlying rocks bake the peat. It turns into lignite or brown coal, that's a bit better. Then it cooks more and turns into subbituminous coal. And finally, after a very long time, it becomes high-quality bituminous coal and eventually anthracite.
That's the good stuff.
That is the good stuff. That is the energy-dense, high-carbon rock you need for making coke and steel.
So the coal has to cook. It has to mature.
It has to cook. And on Earth, that cooking time was, on average, somewhere between 100 and 300 million years. Now, look at our timeline. The Carboniferous laid down the peat about 300 to 360 million years ago. It spent that whole time cooking. And just as it reached peak maturity, who shows up on the scene?
Homo sapiens. We walked into the kitchen right when the timer went off.
Exactly. We arrived at the perfect moment. But consider the alternative. What if an intelligent species had evolved on Earth much earlier, say in the Triassic period, alongside the first dinosaurs, around 200 million years ago?
A smart dinosaur civilization, the Silurians.
Right. If these intelligent dinosauroids had started digging in the ground looking for fuel, the coal from the Carboniferous would have only been cooking for, maybe 100 or 150 million years?
It would still be lignite or peat. It wouldn't be ready.
Exactly. So they would try to burn it, they would try to build big furnaces and make steel, but the fire wouldn't get hot enough. The fuel would crush under the weight of the ore. They would hit the exact same physical limit we talked about.
And they would probably just give up. They'd conclude it was impossible.
They would be forced to give up. Their entire civilization would be stuck in a pre-industrial state simply because the planet's fuel hadn't finished cooking yet.
That is terrifyingly specific.
Yeah.
So you need the biology to make the trees with lignin. You need the geology of plate tectonics to bury them. You need hundreds of millions of years of time for them to cook. And then you need intelligent life to evolve.
And you need that intelligent life to evolve after the cooking is done, but before the coal is destroyed. Coal seams don't last forever. Over geologic time, they get pushed up by tectonic forces and erode away, or they get subducted back into the mantle. There's a temporal window.
If you miss the window, you miss your chance to go to the stars.
Lincoln Thais, the author, calls it synchronicity. The resources and the user of the resources must coincide in time and space. If they don't, the planet remains silent.
So this brings us back to the search, to the Fermi paradox. If this theory is right, we shouldn't just be listening for radio beeps from the sky. We should be looking for smoke signals.
In a way, yes. The paper suggests a new and very different strategy for searching for ATC's advanced technological civilizations. Instead of just listening, we should be looking at the atmospheres of exoplanets for the chemical signatures of an industrial revolution.
What does an industrial revolution even look like from light years away?
It looks like a chemical mess, a very specific, unnatural mess. If a civilization is burning massive amounts of bituminous coal to bootstrap their technology, their atmosphere is going to be flooded with specific industrial byproducts.
Carbon dioxide obviously would be a big one.
Yes, high levels of CO2. But a planet can have high CO2 naturally. Look at Venus. Its atmosphere is basically all CO2. So that on its own isn't enough to say aliens. You need the whole unnatural mix.
The cocktail of pollutants.
Exactly. You look for high levels of sulfur dioxide from burning sulfur-rich coal. You look for nitrogen oxides from high-temperature combustion. You look for aerosols of heavy metals like mercury and lead. And specifically, you look for soot.
Soot. Carbon particulates. Can we actually see soot in an atmosphere from that far away?
With the next generation of space telescopes, the successors to James Webb, yes, it should be possible. We use a technique called transit spectroscopy. We wait for the planet to pass in front of its star from our point of view.
And the starlight filters through the planet's air.
Right, and different chemicals in that air absorb different very specific colors or wavelengths of light. If we analyze that filtered light and see the absorption lines for CO2 and sulfur dioxide and nitrogen oxides and the broad dimming effect of soot all peaking at the same time.
That's a combination that nature doesn't really create on its own.
It's very, very hard for nature to do that.
Right.
Volcanoes produce sulfur and forest fires produce soot, but to see all of them sustained at high levels all at once strongly implies artificial industrial scale combustion.
So we are literally looking for a planet that looks like Pittsburgh in 1920 or Beijing in the early 2000s.
We're looking for a smoggy world, and here is the really tough part, the great filter aspect of this.
Why?
There's a huge catch. The window to spot this is incredibly small.
Because the industrial phase doesn't last forever.
It can't. Think about our own history. We started burning coal heavily in, say, the mid-1800s. We are now, roughly 200 years later, trying as hard as we can to transition away from it. We're moving toward nuclear, solar, and hopefully fusion.
So the smog is just a temporary state of being for a civilization.
Ideally, yes. There are two outcomes for a coal-burning civilization. Either they destroy their planet with the pollution and go extinct, in which case their signal dies out, or they succeed. They use the energy from coal to build the clean tech, and they stop burning the coal.
So either way, the soot clears.
The soot clears. The sulfur dioxide rains out. The signal fades. The authors of the paper estimate that this detectable industrial phase might only last for 500 to 1,000 years, tops.
500 years. In the 4.5 billion year lifespan of a planet, that is a blink of an eye.
It's less than a nanosecond in cosmic time. If the universe is 13.8 billion years old, the odds of us happening to point our telescope at another planet during that specific fleeting 500-year window of its entire history are statistically, well, they're incredibly small.
It's like trying to take a picture of a firework, exactly at the moment it explodes. If you look a second too early, there's nothing but a rocket trail. If you look a second too late, it's just smoke fading away in the dark.
That's a perfect analogy. And this might explain why we haven't found anyone. The primitive civilizations are invisible because they aren't burning anything. And the super advanced civilizations are invisible because they've moved on to clean, sustainable energy sources. We can only see the ones currently in the dirty teenage years of their technological development.
It makes the search feel so much harder.
Yeah.
But in another way, it really refines it. We know exactly what we're looking for now, even if it's rare.
It does. It reframes the Great Silence not as a mystery of biology, but as a challenge of timing.
So let's zoom out. Let's talk about the big picture. What does this all mean for us, for our place in the universe? We used to talk about the rare earth hypothesis as being all about biology. We thought maybe making the first living cell is the hard part.
Right. The great hurdle was always assumed to be the origin of life itself, the jump from non-living chemistry to a reproducing cell.
But this paper kind of flips that on its head. It suggests that, you know what, maybe life is common. There might be planets everywhere with moss and trees and maybe even smart animals running around.
But they're stuck. Think about it. There could be brilliant aquatic civilizations living in global oceans. Creatures as smart as us, maybe even smarter. But can you smelt steel underwater?
No. You can't even build a fire underwater.
Exactly. So they will never build a steam engine. They will never invent the transistor. They will never build a spaceship. They might be incredible philosophers and poets of the deep, but they will never call us.
Or what about civilizations on dry, rocky planets that never had the right kind of plate tectonics? They might have amazing cultures. They might be brilliant astronomers with glass telescopes, looking up at the stars and wondering if they're alone.
But they can't leave. They are trapped by their geology. They lack the starter fluid. They lack the energy density required to escape their own planet's gravity.
That is such a tragic image. Silent worlds full of thoughts and dreams, but completely void of the technology to act on them.
It is tragic, but it's also, in a way, empowering for us. It forces us to look back at our own planet and realize just how incredibly lucky we are.
We really hit the jackpot, the cosmic lottery.
We did. We had the right kind of star, the right distance from it. We had the liquid water, the oxygenic photosynthesis to create biomass. We had the tectonic collision at just the right time to create the basins. We had the biological lag to preserve the wood. We had the hundreds of millions of years of cooking time. And then we evolved at the exact moment the fuel was ready to use.
That is just an unbelievable number of tumblers that had to click into place to unlock the door to the universe.
It is. It suggests that while intelligence might be an inevitable product of evolution on many worlds, technological intelligence might be a profoundly rare and accidental product of geology.
So I want to wrap up with this final thought. We started this whole conversation looking for aliens in the sky, but we ended up staring at a piece of coal here on Earth.
It really changes your perspective on the resource, doesn't it? We rightly demonize fossil fuels today because of the climate crisis. They are the villain of our current story, the Anthropocene. But this research frames them as something else. It frames them as a bridge.
A bridge we had to cross to get where we are now.
A necessary evil, perhaps. A dangerous double-edged sword. But maybe a necessary one. Without those swampy, weird-looking forests 300 million years ago, without that dirty, messy, polluting phase of our history, we would still be on the ground.
We'd be telling stories around a campfire, looking up and wondering what the moon is, instead of having actually walked on it.
Exactly. So the silence of the universe might not be because we are the only ones alive. It might be because we are one of the very, very few who are handed the keys to the library.
We the ones who won the geological lottery. And the terrifying question now is, what do we do with the winnings? Do we burn the house down with the lottery ticket? Or do we use it to finally graduate to the next level of civilization?
That is the question of our time. It's the challenge every technological species, if there are any others, must have faced.
It's a sobering thought. Next time you see a piece of steel or a skyscraper, or even just turn on a light, maybe take a second to remember the millions of years of impossible luck that went into it.
Indeed. Keep looking up at the stars.
But maybe look down at the rocks once in a while, too.